Hello, and welcome to the next episode of Bio-Phi-Cast, where we are going to discuss the future of energy storage. As you may have noticed, form of today's podcast is slightly changed due to a special guest, whom I would like to kindly welcome. Our guest is Dr. Dóra Zalka. Hello.
Hello.
Dr. Dóra Zalka is a beamline scientist at the SOLARIS National Synchrotron Radiation Center in Krakow, where she focuses on tender and hard X-ray absorption spectroscopy, Operando, and in situ battery diagnostics. Also, advanced X-ray data analysis methods. She obtained her PhD in physics from Paweł Józef Szafarik University in Košice, with a focus on lithium-sulfur batteries, electrochemistry, materials science, and synchrotron-based techniques. She has conducted X-ray experiments and developed Operando measurement of battery cells. Dóra has presented her research at leading synchrotron and electrochemistry conferences across Europe: Oxford, Trieste, Grenoble, Budapest, and Karlsruhe. Published extensively in peer-reviewed journals. She is also engaged in scientific software development to improve Xane's interpretation. The first question that comes to mind is, why do we have to bother finding new ways of storing energy? What are the challenges of energy storage?
Thank you for the interesting question. And I think it's a very important topic nowadays because just let's imagine a sunny afternoon when solar panels generate a lot of electricity. But in the evening, when we actually need that energy, the sun is already gone. That's, for example, one of the reasons why we need to have good energy storage systems. The problem is that most current batteries can't store enough energy, or they lose capacity over time, and some of them use expensive or rare materials. We also want batteries that are safe and don't harm the environment, and I think that's a big challenge for engineers and scientists today.
To understand how to store energy, we would have to go into the details of how do modern batteries work.
In most batteries, especially the ones used in your phones or laptops, small particles, called lithium ions, move back and forth between two materials, which we call the cathode and the anode. This movement of the ions through the electrolyte creates electricity. When you plug in your device to charge, the ions move from the cathode to the anode. When you unplug and use it, the ions move back, releasing energy. It's a bit like filling and emptying a tank, but with tiny particles instead of water and electricity instead of fuel. Now, depending on what the battery is used for, the cathode can be made of different materials. Two of the most common are so-called NMC, which stands for lithium nickel manganese cobalt oxide. It's widely used in electric vehicles because it stores a lot of energy. LFP, or lithium iron phosphate, which is more stable and safer and is often used in electric buses or home battery systems. But both have their drawbacks. NMC, for instance, contains cobalt, a rare and expensive metal, often mined under poor working conditions. LFP batteries are heavier and store a bit less energy for the same weight. NMC is, I can compare like high-performance sport car, fast but expensive, and high maintenance. And LFP is more like a sturdy family one, safe and reliable but not as fast. And in general, these batteries still rely on complex manufacturing and non-renewable materials. So even though they work well, researchers like us are going for greener, cheaper and more powerful alternatives like lithium-sulfur batteries.
And what is it that exactly makes lithium-sulfur batteries better than today's batteries?
Lithium-sulfur batteries are kind of like superheroes in the battery world because they can store much more energy per gram than regular lithium-ion batteries, which means a battery could be lighter and cheaper, but still powerful. What's interesting is that lithium-sulfur batteries were actually discovered earlier than lithium-ion batteries back in the 1960s and 70s. And at the same time, the technology wasn't stable enough to use in real products. Most of today's batteries use what we call intercalation. The lithium ions move in and out of the crystal structure of materials like nickel or iron. Lithium-sulfur batteries works in a different way than traditional lithium-ion ones. Lithium-sulfur batteries use a different chemistry called a conversion reaction. Instead of lithium ions just slipping into layered materials, they actually react with sulfur to form new compound called lithium sulfide. This reaction releases 5 times more energy as compared to lithium-ion technology. And scientists are returning to lithium-sulfur technology now because it offers some big advantages. For example, sulfur is cheap, safe, and abundant, unlike rare metals like cobalt. Sulfur is a byproduct of hydrocarbon extraction industries. However, because sulfur is not a good electrical conductor, we have to embed it into the conductive carbon matrix, like a porous sponge, and glue it all together with the binder material. And just an interesting fact, I think this is something really impressive, that 10 years ago, a company called Scion Power provided already lithium-sulfur batteries for a special aircraft called Zephyr 7. It's not your everyday drone, it's a HAPS, which stands for High Altitude Pseudo Satellite. Basically, it flies incredibly high, way above the clouds, and it can stay in the air for over 11 days using only sunlight and these lightweight batteries.
It seems crucial for such device to carry as little weight as possible while maintaining a severe energy intake during the time of its working, right?
Yes, exactly.
Therefore, you've told us about several qualities of such batteries that make them special. Therefore, why aren't they broadly used yet? Why cannot we see them in stores?
Yes, that's a very, very good question. It's a great question. Lithium-sulfur batteries, despite their high theoretical energy density, face several significant challenges that limit their practical implementation and commercialization. I think they are not available in stores because they haven't reached the point of commercial viability yet, primarily due to issues with cycle life and safety. While they offer promising benefits like higher energy density and lower costs, current technology struggles with long-term durability and reliability. One example, I think this is the most important problem, the volume expansion of the sulfur cathode, because sulfur undergoes significant volume change when it reacts with lithium and forms this lithium sulfide, which can strain the cathode and lead to structural damage. Another issue is something called the shuttle effect. During charging and discharging, some sulfur compounds called polysulfides, these are intermediate products, dissolve into the electrolyte and start to shuttle, commutate, move or back and forth between the cathode and the anode. And it's like when sugar dissolves in the tea and spreads everywhere, and these moving molecules waste energy and damage the battery over time. And nowadays, scientists are trying to find ways to stop that shuttle effect and keep everything in place so the battery lasts longer and works more efficiently.
So then, in simple words, how can we make them work? How can we make lithium-sulfur batteries more stable and efficient?
Making lithium-sulfur batteries work well for real-world use is a bit like solving a puzzle. Every piece matters. Two of the most important pieces are the cathode design and the binder material. Let's start with the cathode. Sulfur, while very energy-rich, has a major problem. It doesn't conduct electricity. To make it usable in battery, we have to mix it with a material that can help electrons move. That's where the carbon matrix come in, a kind of sponge-like structure made of tiny carbon particles. This matrix holds the sulfur in place and allows electric current to flow. However, the sulfur doesn't want to stay so easily. During battery operation, sulfur turns into lithium polysulfides, which can dissolve into the electrolyte and wander off. This is the so-called shuttle effect, what I mentioned, and it leads to fast capacity loss. That's why we sometimes use advanced carbon materials like graphene, which has a very high surface area and excellent conductivity. Graphene-based cathodes can help trap the polysulfides better and increase the conductivity of the electrode. But what is the downside? The graphene is still expensive and not easy to scale up, so it's not a perfect solution yet. In our research, we didn't use graphene. We used a material called Super P, which is a type of fine-grained carbon black. It's a very conductive, cheap powder made from tiny carbon particles. It may not sound so high-tech like graphene, but it's widely used in batteries because it provides a good balance between electrical conductivity and ease of processing. And it also acts like an electronic network inside the cathode, helping electrons travel efficiently through the sulfur-carbon mixture. And another advantage of this Super P that it's also scalable and industrially available, making it a practical choice for real applications. In a battery, the binder might sound like a minor component, but it plays a major role. It's the glue that holds all the particles in the electrode together and keeps them attached to the metal current collector as well. The most common binder used today, both in the laboratories and in the industry, is called PVDF, which stands for polyvinylidene fluoride. It's a synthetic polymer, basically a kind of plastic, that works well because it forms strong, stable films. But it has several serious drawbacks. It needs to be dissolved in a toxic solvent called NMP, N-methylpyrrolidone, which is harmful for both humans and the environment. NMP can enter to the environment through emissions to the atmosphere or releases into water as a component of wastewater. From battery point of view, the main issue is that it doesn't interact chemically with the sulfur or lithium. It's just a really passive glue. It's also very rigid, so it can not adapt when the battery expands and contracts during discharge, which causes cracks in the cathode, and it can lead also very huge capacity loss or even failure of the battery. And this is the point where biomaterials come in. They offer a greener, safer and smarter alternative. In our research we used karagen, a natural polymer extracted from red algae. It's commonly used in food products like jelly or plant-based milk as a thickener, but in a battery it offers unique advantages. First of all, it's water-soluble, so we can make electrodes without any toxic solvents, just water. It contains chemical groups like OH groups, hydroxyl groups or ester sulfate groups, which can form real chemical bond with lithium polysulfides. That means it doesn't just glue things together, it actively participates in the battery chemistry, helping trap those wandering sulfur species that cause the shuttle effect. It's also mechanically flexible, so it can absorb volume changes and prevent cracking of the electrode.
Potential side effects of using biomaterials. Example, their impact on electromechanical stability or resistance to charge or discharge cycles. Could karagen react with the electrolyte or break down over time?
Of course, we also have trade-offs. For example, binder performance depends heavily on how much you use. Too little and the electrode falls apart. Too much and it blocks the flow of electrons or lithium ions, which reduces capacity. That's why we tested different karagen ratios. We found that 10% was ideal. It kept the electrode intact, improved cycling stability, and delivered 30% more capacity than PVDF in long-term tests, especially at high charge-discharge rates. To test the reaction with the electrolyte, which is a very good and very important question, we used various techniques like X-ray photoelectron spectroscopy to study the surface of the electrode chemistry, and we used X-ray absorption spectroscopy to track how sulfur species evolved to the electrolyte, and we also used nuclear magnetic resonance spectroscopy. In principle, we put the karagen into the electrolyte solution and we monitorized the dissolution through a couple of days and weeks. We found that karagen doesn't dissolve into the electrolyte, and even after 250 or 1000 charge-discharge cycles, it stays on the electrode and continues to trap polysulfides. In fact, The X-ray absorption spectroscopy confirmed a formation of a new stable sulfur-containing compound in the electrode. That formed just because of the binder's chemical activity. So I should summarize this question that yes, too much binder increase the electrode resistance, and in optimal ratio it can actively participate in the battery chemistry and can deliver a lot of benefits.
Among various candidates for binder material, algae were chosen. What determined this choice?
When it comes to finding a better binder for lithium-sulfur batteries, scientists already tested many natural biopolymers, things like cellulose from plants, chitosan from shells, gelatin from animal proteins, and gums from trees, like gummi arabicum, for instance. But in our research, we turned to the algae, especially the red algae contain this compound called karagen, which is a long-chain sugar molecule. It's a polysaccharide, and it's already widely used in the food industry as a thickener in plant-based milks, as I mentioned. And we know that it's safe, abundant, and biodegradable. Beyond that, it turned out that karagen has ideal chemical properties for batteries because it contains these functional groups, hydroxyl ester sulfate groups, that can bind strongly to lithium polysulfides. And these are these intermediate byproducts that normally cause the failure of the battery. And another attractive property was the karagen, that it's water soluble, so we can use it in eco-friendly, solvent-free processing, no toxic chemicals needed. And we also noticed that it forms flexible, gel-like structures, which help the electrodes survive hundreds or even thousands of charging cycles without falling apart. Another reason we choose karagen is that it comes from a renewable source. Red algae grow in oceans without needing fresh water, pesticides, or agricultural land, and they are actually considered as marine waste. So in terms of sustainability and scalability, it's a very attractive option.
And what may be the other technological challenges with using karagen as a binder? You've mentioned issues with the compatibility. Is there more to that? For example, how does it affect battery lifespan and how much energy can it store?
When we tested the electrodes with this karagen, they achieved actually 30% more capacity than the standard PVDF-based electrodes, what the industry uses. And we noticed that they could last and survive 1,000 fast charge-discharge cycles, which is quite unique in field of lithium-sulfur batteries because they are not tolerate so well this half-an-hour fast charge and discharge cycles. And we achieved 70% capacity retention with this ultra-fast charging, which is quite outstanding results for lithium-sulfur batteries.
Another interesting perspective is, does karagen remain stable under battery operating conditions such as high temperature and humidity?
This is a very important question for real-world application, especially if batteries are going to be used in electric vehicles or solar energy storage, where temperatures can get quite high. Our experiments show that karagen remains mechanically stable during hundreds of cycles because it stretches and bends with the electrode rather than cracking, and forms a stable chemical interface as we see in our X-ray spectroscopy measurements. We also monitored its performance under intense cycling and elevated conditions, and it held up very well. However, full testing under, for instance, high humidity and high temperature storage is still ongoing in the field, and different battery configurations might yield different results. So it's still under investigation, let's say. But so far, no major degradation has been observed. But like all biopolymers, karagen will need to be validated before it can be used in commercial batteries.
About the validation, what is the current state of research and prototype testing?
In our case, this karagen-based binder isn't just something what we tested in small coin-type cells level. it's already been tried out in large pouch cell prototypes. My previous research group in Košice, Slovakia, led by Dr. Andrea Strakova-Fedorkova, collaborated with the Ukrainian State University of Chemical Technology, and they also compared this 10% karagen and 10% PVDF containing batteries under cycling conditions, and they run the pouch cells for 70 charge-discharge cycles at different speeds of charging and discharging. And it turned out that the PVDF, what the industry uses, lost 83% of its capacity, especially at higher charge rates. In contrast, the battery with karagen only lost 7% of its capacity overall. So these results match very well what we saw in our smaller coin cells, confirming that the performance of karagen holds up even at a larger scale. I should say that it even performed better in larger scale as in the small coin type cells. So I think that's a big step forward toward real-world applications.
And do you have any examples which sectors could they be used for? Automotive or consumer electronics?
At pouch cell level, it can be applied in consumer, military, as well as automotive industries. I should notice here that no standardized pouch cells exist. So each manufacturer builds the cells for a specific application. And as I mentioned, the lithium-sulfur batteries are light in weight, so they are promising candidates also for aviation, satellites, military equipment, and space technology.
Would you be able to name the steps that are necessary to move from laboratory testing to mass production?
To answer this, I actually spoke with Mikolaj Golunski, the industrial liaison officer at Solaris Synchrotron, where I'm currently working, and we discussed two main possibilities, two main possible pathways forward. The first option would be collaborate with already existing startups for battery manufacturers. I should notice here that in Europe, nowadays there are minimum 4 or 5 startups who are trying to commercialize lithium-sulfur batteries. So in that phase, it can happen that we can convince a company that already works in energy storage to adopt our technology. In that case, I could contribute, for instance, as a scientific advisor, helping them implement and optimize the binder and electrode materials at a production scale. Another way, and I think this is harder way to go, establish a new spin-off company through grant support. This option is starts with applying for a national or international innovation grant to launch a startup for our own. That would mean assembling a small team and securing funding, especially to cover the initial investment in machines, production lines, and workforce. Setting up manufacturing infrastructure is expensive, so early financial support is critical in that situation. But the good news that our cathode production method is already industrial friendly. It means that we use only standard, low-cost, and commercially available materials like sulfur, what I mentioned, a byproduct of the petroleum industry, also byproduct of the mining industry, so it's very abundant element. Carbon black, the conductive matrix commonly used already in all battery types, and karagen, it's already widely produced in the food industry. So we don't need to reinvent the wheel how to produce this karagen because it's already used widely in our everyday life. And water as the solvent. So it is also very easy to have, and it doesn't contain any toxic material. This means that we don't have the typical obstacles in scale-up, like, I don't know, sourcing some rare element or reproducing complex synthesis methods. I made actually a very conscious decision not to use graphene or any expensive chemical steps, precisely to keep the process simple, affordable, and ready for industrial translation. I think that's the thing which makes this research quite unique.
And for closure, if you would kindly like to answer what seems to be maybe more of a personal question. Lithium sulfur batteries were your PhD project, right?
Yes,
so
exactly.
Therefore, how you ended up in our Jagiellonian University due to this path of scientific way?
Yes, it's a very interesting question. When I was working with the batteries and I noticed this unique electrochemical behavior, I'm a scientist. Of course, I was curious and I wanted to understand why they are performing so well. And okay, we had initially a conception that probably because the karagen reacts with these intermediaries, but I needed to have some confirmation. And this is the point where Solaris synchrotron came into the picture, because I applied for beam time to an X-ray absorption beamline at Solaris called Astra beamline. And I started to work with the team in 2022 already. And I participated in many beam times where I measured lithium sulfur batteries during charge and discharging them with X-rays. And I was able to penetrate with the X-rays to the whole battery volume and follow during charge discharge in real time the chemical reaction inside the battery. And it was quite unique. We were the first on the world who performed this in such a low energy where sulfur is measurable with X-rays. So it was not an easy task to design a special electrochemical cell which still keeps the original battery performance, but also compatible with the X-rays. And from that reason, I spent here in Krakow 2 months as internship, and I was working very intensively in these measurements. And then I somehow stuck in the synchrotron because after these experiments, there was no question for me that I also want to be a beamline scientist, because it's a very exciting job to help researchers to design sometimes very complicated setups and help them to solve their puzzle, help them to answer the questions. And I think with my quite multidisciplinary background, I can help biologists, physicists, chemists who are arrived to the Solaris synchrotron and they have questions regarding their materials.
Thank you very much, Dr. Zalka, for introducing us to yet another appliance of biomaterials in today's episode.
Thank you very much for the possibility to talk, and I think what you are doing with this podcast is super important, because I think nowadays it's crucial to bring the science closer to the people and really talk about what we are doing, why we are doing, how we are doing, and I really appreciate your work with this podcast, and thank you once again to be here.
Thank you very much. That's our goal. I would also kindly like to thank all of our listeners, and I would encourage all of you, our listeners, to check out other episodes of our podcast that link different fields connected to biophysics. Thank you very much. Today, the voice of the podcast was Marianna Grabowska.